Okay, so the recording will start soon. That works. Okay, so yeah, where was I? So as a quick reminder, if you're going to multiply fractions, let's say 2 over 5 times 7 over 3, in the top right here, you're going to the rule is for multiplication is top by top divided by bottom. So if you wanted to multiply this, you would do 2 times 7 over 5 times 3. Two times 7 is 14. Whoops, sorry, I pressed the button on the iPad. 5 times 3 is 15. So 14 over 15 would be your answer. The same principle applies to when it's not numbers, but x's or y's or whatever you might find in here for a rational expression. It's 3x times x minus 1 divided by x plus 1 times x plus 2. Now, you could multiply this out, but most of the time you prefer things to be in a factored form because generally factored forms are nicer. You can see if there's any cancellations or any reductions in the expression, but just for the sake of this one, I'm going to just multiply it out. Multiplying out, you get 3x squared minus 3x divided by x squared plus 3x plus 2. So the multiplication of rational expressions works the exact same way as multiplication of numbers. If we had division, let's suppose we had 3x divided by x plus 1. Okay, again, the division sign is not something you see too often. It's normally like a big big kind of fraction that you more so see written in a complex fraction. But the division works just like it would for numbers as well. So let's say you had 2 over 5 divided by 7 over 3 again, or well, this time divided by. You remember how you would approach this? So you would just take the dividing term, the 7 over 3 here, and flip it and multiply instead. So the rule that you think of in your mind when you're going to divide a fraction by another fraction is you take the dividing fraction, the second one, and you flip it and multiply instead. So now multiplying the same operation as before, 2 times 3 is 6, 5 times 7 is 35. Well, the same thing happens here when it's division of rational expressions. It's going to be 3x over x plus 1, but we're going to take that dividing term, the x plus 1 divided by x plus 2, flip it and multiply instead. So the division symbol became the multiplication sign, and the dividing term got flipped. So take the reciprocal instead. Now we just have, let me just connect these as well. Now we just have another multiplication problem. So 3x times x plus 2 is going to be 3x squared plus 6x. X plus 1 times x plus 1 is going to be x squared plus 2x plus 1. Okay. So hopefully that's something that that you remember pretty well from before. Any questions so far? Okay. So before I go on, yeah, so because you're not using your Ontario Tech email addresses, actually before I go any further, do you have Ontario Tech email addresses yet? Anyone put a yes in the chat if you have them yet? Some do and some don't. That's strange. Still having issues. Okay, if you do have your Ontario Tech email, when you're joining this call, when you click the link to join, you'll probably default to your personal Google account. whatever it might be, whatever email address that we're receiving correspondence from in the beginning. But there's a little button underneath in the top right where you can click switch account. So if you've logged into your Ontario Tech email in your browser, that account should be saved in your browser, and you should switch that one before you join this call. Only because every time somebody joins it, I get a notification to admit you from the waiting room. And I've been getting these notifications every 20 or 30 seconds since class started until a few minutes ago. So in future, if you have the Ontario Tech email account, use it. If you're having issues with it, contact Continuous Learning. I think Nicola Fromm is the person that you'll probably see the most from Continuous Learning. So send her an email and say that you're having issues with your account and it's not working or whatever the issue might be. And as well, be on time for the class. I might stop admitting people after like 10:05, after a 5-minute grace period. Nicola Fromm, have you received communication from a woman named Nicola Fromm yet? I get some yeses in the chat if you have. You must have. Okay. So Nicola Fromm is her name. You should find her in your emails. So if you, I'll write the name in the chat here. So you should see some emails from her in your inbox. If your Ontario Tech email is not working, you should get in touch with her and say it's not working, and then explain what's happening or whatever. Okay. But be on time for class in future. The constant admit for the first 10 minutes of class gets kind of annoying, okay? Okay, so there are no questions about multiplication or division of rational expressions. We're good with that? They work just like numbers. For multiplication, top by top, bottom by bottom. For division, you flip and then do multiplication. Okay. Okay, so let's look at addition and subtraction. Rational expressions. Okay, so again, this is going to work like it would with numbers. So recall with numbers. Let's suppose you wanted to add, say, 3/5 plus 7/2. Well, what you would do is you would say, okay, I need to have the same denominator before I can add these two. And the denominator that I want to use is going to be the lowest common multiple or the least common multiple of the denominators that are currently present. So what you're thinking here is that you want the LCM the lowest common multiple of 5 and 2. Now that number, it's an easy one, we're just doing numbers, right? So the lowest common multiple of 5 and 2 is 10. So it is 10. So you want to multiply, you want to take the 3/5 and the 7/2 and do something to them so that instead of being over 5 and over 2, both of them are over 10. And what you have to do is you have to multiply them by the same thing on top and on bottom. So in your head, you're thinking, what do I multiply by 5 to get to 10? Well, that has to be a 2. And whatever I multiply to the bottom, I also have to multiply to the top. Here I am using the x, like I said, that we don't really do anymore. So I'm going to be consistent here. You multiply the 2 on the top and the 2 on the bottom. That will get your denominator on the first term to be 10. And how do you make the denominator on the second term, the 2 be 10? Well, you have to multiply it by 5. Now, when you do that, you haven't actually changed either of these terms because 2 over 2 and 5 over 5, those are both just 1. So all you've done is multiplied both of those terms by 1, not changing them at all. So 2 times 3 is 6, 2 times 5 is 10, 7 times 5 is 35, 2 times 5 is 10 as we wanted. So we have the same denominator like we wanted. And now you can just combine them because they have the same denominator. So it's 6 plus 35, which is 41. So 41 over 10 would be your answer. So again, I'm not going to stay on numbers too long because we're going straight to expressions, but quick reminder of how you would add two fractions when they have different denominators. So the same approach, again, is what you're going to do when it's an expression, not just numbers, but you have x's or y's or both. So I'm just going to note that it's the same approach when we don't just have numbers. So, for example, suppose we are trying to add x minus 2 over x plus 3 plus x minus 5 over x minus 3. Well, it's the same kind of thing you want to do. They have different denominators, so those denominators have to be the same. And you want to use the lowest common multiple of x plus 3 and x minus 3. So this question is a little simpler to start off. But the lowest common multiple of x plus 3 times x plus 3 and x minus 3. Anyone know what would that be if you can write it in the chat? What would be the lowest common multiple of x plus 3 and x minus 3? Yes, Ayush, exactly. It's just the product of the two. So the idea of the lowest common multiple, in the next example, it'll be a little different, but in this one, it's just going to be the product of the two. So, okay, let's spread this out and give ourselves a little bit of room here. So we have x minus 2 times x plus 3 plus x minus 5 over x minus 3. So that lowest common multiple that Ayush has put in the chat, I want that to be in the denominator of both terms before I make the addition. So when I'm looking at that that's in the chat, I'm saying, okay, this term here, this x plus 3, that is missing the x minus 3. So I need to multiply by x minus 3 to make it work. But whatever I do to the bottom, I also have to do to the top. Otherwise, I'm breaking a rule. If I don't do the same thing to the top as I do to the bottom, then I'm no longer multiplying it by 1. I'm multiplying it by something else, and that changes it. I'm not allowed to actually change the value of it. I'm only allowed to kind of manipulate how it looks a little bit. I'm multiplying it by 1, which doesn't change anything. And that 1 is x minus 3 over x minus 3, because as you can imagine, those would cancel and just leave you at 1. Okay, the other term over here, the second term, it already has the x minus 3, but it's missing the x plus 3. So that's what I have to multiply over here. Now, if I multiply on the bottom by x plus 3, I also have to multiply on the top by x plus 3. Okay? So, now that that is done and they have the same denominator, what we can do is add the numerators and put them over that same denominator, x plus 3 times x minus 3. So what's in the numerator? We have x minus 2 times x minus 3 plus x minus 5 times x plus 3. Okay, so we're not finished yet. We have added the two rational expressions, but it's possible that there is some cancellations to be made. Now, in this form, we can't go ahead and make any cancellations. So for example, if I was to go ahead and say, oh look, there's an x plus 3 and here's an x plus 3, that's not allowed because of this plus sign here. The x plus 3 in the bottom is a factor, but the x plus 3 in top is not a factor because it doesn't multiply by everything else. That plus sign in the middle means it's not a factor. So this cancellation cannot be made. But it doesn't mean the cancellations aren't possible. So what I have to do just to make sure that I can't simplify this anymore is to multiply out all that numerator and then try to refactor it and see if any cancellations appear after that. So I want that numerator in a factored form in order to see if there's any cancellations. Maybe there is, maybe there isn't. As it looks right now, I can't tell. Okay, so what we're going to do is multiply out this term here and this term here. Add up all the like terms. So when we multiply out each of those terms, we're going to see x squared terms, x terms, and number terms in the numerator. We're going to add the common things. We're going to add the x squareds, add the x's, add the numbers, and then we're going to have a trinomial left. And we're going to try to factor the trinomial. Now, it might not work. We might just be left with something awkward, but we have to try and see if it'll simplify. So multiplying out on the first term, we get x squared minus 3x minus 2x plus 6 plus x squared plus 3x minus 5x minus 15. Now, I actually don't want to multiply out the denominator. I quite like that as x plus 3 times x minus 3, because once I'm finished my work on top, if it factors again, I'll want to see if the factors can cancel. But if I multiply out that x plus 3 times x minus 3 into x squared minus 9, I'll just have to refactor it again later to see if it works. Okay? So I like things in a factored form, so I'm not going to multiply out that one. Are there any questions so far? At any moment, feel free to just put a question in the chat. And if it's a little awkward, just unmute and ask a question. Okay. Okay, so adding up those like terms, we have an x squared and an x squared is a 2x squared. I see a negative 3x and a positive 3x. Those two will cancel each other. Minus 2x minus 5x is minus 7x. And plus 6 minus 15 is minus 9. Okay, so now that it's back to a regular kind of looking trinomial, we're going to try and factor it again. So you remember how to factor these? We covered it in the first class. We had a refresher on these kind of ones. We want, let me just write some notes here. So at this point, we need to factor the numerator. Whoops, sorry. To see if any cancellations can be made. Okay, so recall factoring trinomials like this. So we have 2x squared minus 7x minus 9. What we do is we say 2 times negative 9 is negative 18. And we want numbers multiplying to minus 18, that add to minus 7. That was a technique for when you have a trinomial that isn't just x squared plus stuff, it's 2x squared or 3x squared plus stuff like that. You have to multiply the term on the x squared by the constant. And that is the thing that you want multiplying, you want the two numbers to multiply to make. Okay, numbers that multiply to make negative 18 and add to make negative 7. Does anyone know what those are? If you're awake. 9 and minus 2 and 9. Everyone agree? Jasmine's car mistake. Stephen got there. Wasn't has it as well. That's right, yeah. Minus 9 and plus 2 is what you want. Yeah, Lewis got it as well. Yeah. Okay, very good. So yeah, you had the signs the wrong way around. So that's what we're going to use. We're going to use, so let me see, those numbers are minus 9 plus 2. So what we're going to do is say that 2x squared minus 7x minus 9. This is again how it's a little different to the trinomials that you, the trinomials that don't have the number in front of the x squared. You don't just kind of drop them into position in brackets. They're the numbers that you use to break up that minus 7x. Minus 2 and plus 9. And now you're going to do factor by grouping that we also covered in the last class. So the factoring, you want to make sure that you're really, really quick and solid with the factoring, because it just kind of persists through the whole course and in the background of a lot of the maths that you do in calculus and in algebra. You want to just have this ability with, you know, algebraic kind of manipulations just down, so that when it comes time in calculus that you're not stuck, you're not spending your energy going, is this how to do it, and getting tired by doing the factoring. That stuff is just like reciting the alphabet for you. You're just like, la la la, I'm just writing the answer. And you save your brain power for the calculus, for the harder stuff. And all it takes is a bit of practice with this to get really fluid and quick with it. So even anybody in the class here who feels very, very comfortable with this factoring that we covered in class 1, they can tell you as well that it feels good to just be quick with that, not have to worry about it. And then when something harder comes along, you can say, you know, I'm solid, I have the foundations, so I can just worry about the hard stuff and not worry that I won't be able to do some of the mechanics. It feels good that way. But if this stuff is shaky and you're not sure and you're mixing up techniques and you don't know how to do it, and then more hard stuff gets put onto it, it's just kind of stressful, and you don't really want it. So do put in the time. It might feel easy, the chapter 1 stuff, but do put in the time and make sure that it's really, really just easy, quick, no problem. Okay. So we're going to factor by grouping here. It's going to be 2x times x plus 1 minus 9 times x plus 1, which is factored a little further then. And the x plus 1 can come out, and we have 2x minus 9. Okay, so this was a big, what's the word? Kind of aside. So that was just some work on the numerator. If you remember, the problem that we were solving was we were adding two rational expressions. We had gotten it as far as here and said, oh, we need to factor that. So everything we've been talking about there, that factoring we've been reminding of, that's everything we've just been talking about. So going back to it now, that numerator that we just worked out was going to be x plus 1 times 2x minus 9. The denominator all along was x plus 3 times x, whoops, not x minus 1, x minus 3. So we did all that factoring to try to find out if there was any more simplification that needed to be done. There was no more to do because it didn't work. We couldn't factor any further. No cancellations possible. So we're finished. Okay. Any questions here? Okay. We're sure we're all comfortable here? No questions? Okay. All right, well then, what I'm going to do here is we're going to move on. But I want you to work a little bit ahead of me here. I'm going to pause here for a second. Maybe for 2 or 3 minutes and let you try to solve this one before I get to it. Okay. So, okay, good. So get started on this one right here now, and I will wait and let you get started on it yourselves. Then I'm going to go through it. And if I'm taking any different turns that you took in your way to solving it, please ask the question if you have one, or tell me what you did differently, and I'll see if it can be done that way, or if there's something wrong or whatever. So get started on this one, and then I'm going to do the problem myself. Okay. In my estimation, you should be maybe over the halfway point at least, or close to finishing. Can anyone put a yes in the chat if you're finished? Very good, Eric. Okay, Eric, what was the first thing that you did?
So I multiplied x plus 3 and x squared minus x minus x.
So you did, so let me just put this in blue for a second here. So what you did was you said you needed the same denominator.
Yeah.
So you multiplied these together like this.
Yeah.
Okay. That would work. It would get you to the right answer in the end. But does anybody have a suggestion to do something different before you combine? Go ahead, Ayush.
Yeah, so I factored the x squared minus x minus 6 first.
That's the better start. So factor the left denominator. Yes, Evan, you have it in the chat there as well. Yeah, Eric, so the best thing, the key word here that you're thinking about when you're going to start this off is you want the lowest common multiple, or least common multiple. I'm not sure which terminology that you use in school, of the two denominators. And it turns out that when you factor that first denominator, this factors into x minus 3 times x plus 2. Wait. Did I take the question down wrong? I did take it down wrong. My apologies for anybody that is finished. I wanted an x minus 3 here. Okay, Eric, your approach is actually just fine because I wrote the question down wrong at the beginning. I wanted a cancellation to happen here. In the way the question was currently written, factoring first or not factoring first doesn't matter because you wouldn't actually get a lower common multiple than in the beginning. But yeah, in this format, you do want to do that factoring check first anyway, because you want the least common multiple of the denominators. You don't just want to multiply everything together. So the analog of this with numbers, so for a second, let's just think about numbers. Let's say we were going to do 1 over 50 plus 1 over 100. What you're kind of suggesting is to say, all right, well, I'm just going to do 50 multiplied by 100 as my denominator. It's not really the most, the best way to do it because you can just multiply here above and below by 2, and then you have a much lower common multiple of the denominators. So that's kind of what we did with the first term there. Instead of just multiplying the two together, you factor denominators as much as possible, and then see which factors are missing. Did I see a raised hand while I was talking there? Might have been Jamal. Are you here, Jamal? I think you left the call right after. Maybe internet troubles. No one had a question or anything? Okay. Okay, so now, oh, it was an accident, no worries. So now in order to make it work, I just need to multiply over here by x plus 2 over x plus 2. So apologies for anybody, I wrote down the question wrong the first time so that this point wasn't able to be made. You always want to factor denominators before you start, just to make sure that it's going to work out. Now we have the same least common multiple of the denominators. So it's going to be minus 5 plus 1 times x plus 2 all over x minus 3 times x plus 2. So minus 5, 1 times x plus 2 is just x plus 2. And then minus 2 plus 5 is minus 3. And now a cancellation can be made. X minus 3 is the entire numerator here, so it is a factor. It's like, so when you think of the word factor, you're thinking of it as it's multiplying by something else in the entire thing. Like the factors of, say, 12 can be 3 and 4 because 4 is multiplied by something to make 12. Well, x minus 3 can be multiplied by 1 to make the entire numerator x minus 3. So the numerator itself on its own is a factor and you can cancel it in that way. And you have just 1 over x plus 2 left. And that's it in its fully simplified form. Okay. Are there any questions? Just for my own knowledge, does your teachers call it lowest common multiple or least common multiple? Which one is familiar to you? Oh, least. Okay. Lowest for other people. Least for some people. Lowest, least. Okay, so could be either then. That's good. I think I used lowest more frequently than I use least. So you'll know what I mean if I say lowest. Lowest common factor. You normally talk about highest common factor. Here you go, Lewis. Is that fair enough? You normally talk about highest common factor more so than it's usually lowest common multiple and highest common factor. But I guess because the lowest common factor of two things would always be 1, wouldn't it? Like if you think of the factors of 6, 1, 2, 3, 6, the factors of 8, 1, 2, 4, 8. So the lowest common factor would always just be 1 between two things. You're probably lowest common multiple, highest common factor are the things you would think of. Okay. Lewis was just catching up. Everyone can give me a number in the chat from 1 to 5, where 1 is not comfortable at all, 5 is totally comfortable, and 2, 3, and 4 are some kind of way in between. How do you feel about addition or subtraction of rational expressions? 1, 2, 3, 4, 5. 1 for best. Sorry, 1 for worst, 5 for best. Like a quick little poll. Almost, yeah. Yeah, I know how you feel, Eric. Sometimes you're just sort of, you just need to do that bit of practice to get there. 3 to 4, medium. Okay, that's generally pretty positive. Can do one more example before we move on. I'm just checking the time because there's quite a bit to get through today. 10:50. I think we have time for one more. So what I might do is get you to the multiplication and division is, I think, a little easier. With this one, the factoring and the questions get a little longer. I want to focus on the addition and subtraction. So some of the questions I took were from this part. Page. What page is this? I can't even see the page number. Page 19. So you can find the solutions on page 20 if you just missed something here. So I'm just going down to the you have a question, Franklin? You're on mute there. Do you have a question, Franklin? Let's mute. Okay. So, okay, somebody want to give it a 3. Lexi, do you want to pick one of the questions from, say, 20 to 25 for us to cover in class today?
20.
20, okay. So I better write it down somewhere before I move on. 3 over x plus 1. So this is just from the exercise section. You can practice the rest of them yourselves. Okay. So question 20 from exercises. I forget what page or what section number right now, but hopefully you'll know where it came from. So it was 3 over x plus 1 minus 1 over 2x plus 1. Okay, so I'm looking for the lowest common multiple of x plus 1 and 2x plus 1. These are both just linear factors in that there's an invisible little power of 1 on the x's here. That's where linear comes from, because if you were to draw y equals x plus 1 or y equals x2 plus 1, it would be a straight line. That's where that word linear comes from for these factors. And when you're factoring something, getting it as far as linear factors is really what you're after. So both of these denominators are in kind of their lowest form. They're just linear factors, and they're not common with one another. X plus 1 and 2x plus 1 are just different. Evan, yeah, we might have time. I'll flip back to it in a second. So, okay, the lowest common multiple that we want here, this time there's no factoring to be done, it's just right there. Is to just multiply the two factors together. So the 3, this one here would have to be multiplied by 2x plus 1 and 2x plus 1 for it to work. And this one would have to be multiplied by x plus 1 and x plus 1. That's going to get us our lowest common multiple of the two denominators, and that's where we go from here. So 3 times 2x plus 1 minus 1 times x plus 1. 3 times 2x is 6x, 3 times 1 is 3, minus x minus 1. So this minus sign right here is going to distribute in onto both terms. Don't forget to do that. If you ever see a minus sign outside of brackets like that, it has to distribute in. We have x plus 1 times 2x plus 1 at the bottom. And 6x minus x is 5x. 3 minus 1 is 2. Looks like it's not going to cancel or simplify any further. And we're actually ready to stop here. Okay, that one did not take that long at all. So I will go back and do the one that Evan wanted. So which number were you looking at, Evan? 12. Oh, a bunch of brackets. Okay. So that's 50. Minus 25. Hopefully I've taken this down correctly. 4 minus 50 is 25. Okay. So let's go back and see what we get for this one. This was x by x by 8x minus 4 minus 50 plus 25 4x squared minus 25. Okay, so yeah, when you're looking at a problem like this one, and there's layers to it, where you have brackets and brackets inside and stuff happening inside. The best thing to do is start from the inside and work your way out. So the first thing that I'm looking at that I want to sort out is that there. Just to get rid of some of those brackets. So that's going to be x times, multiplying that in, it's 8x squared minus 4x. 4x squared minus 25. Okay. There should be a key word coming to mind when you see that we're going to leave for later. Might look like something from your quiz. Factoring technique. Okay, and let's see what else we can do. I see more brackets on top, so I'm inclined to multiply those out. X times 8x squared is 8x cubed. X times 4x is 4x squared. Minus 50x plus 25 over 4x squared minus 25. So The reason that I took those 2 steps to multiply them out like that is because to simplify and to do those kind of operations that you want to do, I want the numerator and the denominator in factored forms to see if I can make any cancellations and reduce the whole thing. Now, in that first form at the top of the page, that's not a factored form because the plus 25 on the outside is making it not be in a factored form. Right now, we have it in the form of a what do we call those? It's not a trinomial. I guess it's just an expression with 4 terms. A quadrinomial or something would be the proper term for it. But I'm looking to factor right now. Now, the denominator looks like a difference of squares, and the numerator, well, hopefully factor by grouping works because that's the only technique we have to factor something like that. So let's see if we can factor that by grouping. The groups that they're currently in look like they might work. 8x cubed and 4x squared. We have x squared in common, and 8 and 4 both have numbers in common. 50 and 25 have numbers in common. So let's see if we can do that one. So, okay, factoring out 4x squared from the first 2 groups, you're going to be left with 2x minus 1. Okay. So that is factoring this here. And factoring the second one now. Let me just... Factoring the second one. All I see is there's an x and there's a no x in the second term. So x won't come out. But we want whatever number, the highest common factor of 50 and 25, which is 25. And we would rather take out minus 25 because that will leave us with a 2x minus 1 in here, which matches the factor in the first term. So this gets factored in this way. And on the bottom, we have 4x squared minus 25. 2x minus 1 is common. When we pull that out, we're left with 4x squared in the first term and just minus 25 in the second term. And actually, it looks like we never even had to factor the denominator because now we have 4x squared minus 25 on top, 4x squared minus 25 on the bottom, just leaving us with 2x minus 1. So the final answer for this one, as nasty as it looked when it started, this x times 8x minus 4 minus 50 plus 25 and so on, all divided by 4x minus 25, simplified all the way down into 2x minus 1. So just a little more about the thought process there. At first glance, when I see this problem, I'm looking at the denominator of 4x squared minus 25, and just in my own head here, a little alarm bell is going off thinking that this is going to be 2x plus 5 times 2x minus 5. And I'm just thinking this might be helpful. Oops, I keep hitting that button. Might be helpful later. Now, it turned out that it wasn't helpful, but that's just something that was in my head as I saw it. It might be just helpful to know that for some of you. For example, if this term here, the 4x squared minus 25, this term here, if that turned out to be 2x minus 5 times 2x plus 7 or something, then it would have been good to have it in a factored format. Oh, back to question 20. Yeah. Any questions about the last 2 problems that we just did? No problem, Jasmine. Okay, so as I saw there a second ago, tons of problems for you to practice. I've done a few of them there, but lots and lots more. you should be running through all these, making sure that you can do them and that you're not getting stuck, or that you're comfortable enough by the time you finish them. So unless there's any questions about rational expressions, addition, subtraction, or whatever, I'm going to move on to radical expressions right now. Sure there's no more questions? Okay. Moving on to radicals then. So these are expressions that have square roots involved. Not just square roots necessarily, cube roots, fifth roots, and so on. But we're just going to focus on square roots for now. So again, be aware of the text that has everything you need to know in here. So scrolling on. So when simplifying radical expressions or expressions with root symbols, and in particular, I'm referring to square roots here. The three things that you have to watch out for and that you have to try and simplify or manipulate away so that it's in its most simple form. There's no square factor underneath a square root. So for example, if you're looking at something like square root of 20, what are the factors of 20? 1, 2, 4, 5, 10, 20. Now, are any of those numbers a square number? Is it like a perfect square? Yes. 4 is a factor in there, and 4 is 2 squared. So you try to extract that from underneath the square root. So for that 20, the factor pairing that you're going to go for here is 4 by 5 instead of 2 by 10, because 4 by 5 is the pairing that has the square factor. One of the properties of square roots is that you can take this step here. If you have two things multiplying inside 4 by 5, you can split the square root over each one. It's going to be the square root of 4 times the square root of 5. And the square root of 4 is 2. So the simplified form of square root of 20 is 2 times root 5. And that's what you're going to need to do if you see numbers that have square factors that can be extracted. That's something you have to do in the simplification process, is you have to bring it outside. Another thing you have to watch out for is that there's no fractions inside the square roots. For example, if you see something like the square root of 1/5, square root of 1/5, that's a fraction symbol underneath the square root, so you simplify. Again, you have this property that square root of 1/5 is the square root of 1 over the square root of 5. That is one of the other properties that you can use. You know what, maybe I'm just going to fill in a little general property here. If you have the square root of a times b, that's the square root of a times the square root of b. That's something that was used here. And in this highlighted one here, if you have the square root of a over b, that is the square root of a over the square root of b. Those are the properties that got used there. So, and the square root of 1 is just 1, so it's 1 over root 5. And the final property that you're going to look at, or the final thing that you need to simplify, is that if you have a square root in the denominator, you want to get square roots out of the denominators. There should only be square roots in numerators. So we're continuing where we left off. We had 1 over root 5. The way that you can get rid of that is you multiply above and below by root 5. So root 5 over root 5, that is just 1. Really, all you've done is multiply 1 over root 5 by 1. The square root of 5, just change the square root of 5 by the square root of 5, that is just 5. And now you've taken the square root out of the denominator. It's root 5 over 5 now. Okay? Are there any questions about those? Everyone confident enough on those? So what we're going to be doing for the next little while is we're going to have some expressions. There might be numbers or x's and y's or who knows what, with square roots involved, maybe fractions as well, or rational things as well. And we're going to be trying to simplify them. So we're going to be There might be addition of fractions going on or rational expressions. There might be square roots in there now instead of just x's and x squareds. And we're going to be trying to make sure that we're leaving things in their most simplified forms. That is no square factors under roots, no fractions under the roots, and no square roots in the denominator. Okay, so there's a bunch of examples here. I've picked a few of them that I'm going to go through separately to the text. But again, if you don't get something taken down, you can see the steps of them here in the book as well. So I'm going to just back out. Whoops. I'll just back out here and continue on. So as a quick reminder, the rules. No square factors under the root. It's a pretty ugly square root. Let me try again. We also had a rule, no fractions I shouldn't use under. I'm trying to write a kind of shorthand here, but I have to be careful. Inside the square root, and no roots in the denominator. So those are the things that we're watching out for and the things that we're going to try and correct in our simplification process. Okay, so let's simplify the following. Root 3 times root 12. Can anybody tell me what I should do here to simplify this? What's standing out to you as a starting point? Feel free to unmute if it's awkward in the chat. Ideas? Go ahead, Lewis.
In my case, I will separate the square root of 12 in square root of 4 and the square root of 3.
Perfect. And why'd you do that?
So in that case, I can separate them, and then I have square root of 4, which I can get 2, and then I can multiply the two square roots of 3 and get square root of 9 and get a 3.
Very good. Yeah, that's exactly it. So Lewis spotted that 12 has a square factor. The factors of 12 that come to mind, you've got 1, 2, 3, 4, 6, and 12. 1 by 12, 2 by 6, 3 by 4. But if you look at it as 3 by 4, 4 is a square number. 4 is 2 squared. So you want to change that 12 to 4 times 3 and do something about that 2 squared. So this is root 3. Square root of 4 is 2 times root 3. So one thing that you can do just to make this look a little nicer, bring the 2 out to the front here. We have 2 times root 3 times root 3. And the last thing is that root 3 times root 3, that is just 3. So your final answer is 6. So root 3 times root 12 is actually just 6. You see things with square roots here, and they it looks like it might be some nasty decimal number, but with a little simplification, it turns out it's just 6 after all. Okay. How about square root of 240? So what you're trying to figure out here is a way to reduce this 240. You're thinking maybe there's a square factor, maybe there's not. If you're good with numbers, if you're good with kind of mental math that way with multiplication and numbers and division and stuff like this, You might just be able to look at this and pick out and say what the square factors are. Could you multiply the 3's to make square 9? Yes, yeah, that's what you could do, Zariah. So you could combine this to be 3 times 3, which is the square root of 9, which is 3. That works. Yeah, I think for me, by habit now, I'm kind of thinking that if I see the square root of a times the square root of a, that's just going to be a. It's kind of as much a memory thing for me now as anything else. But yeah, that's kind of what's going on in the background. Okay, so when it's a big number like this, so going back to the square root of 240, you're trying to figure out what the square factor, if there is a square factor, or if there's not. So what some people like to do, I'm actually blanking a little bit right now on what the largest square factor is, so I'm going to go through a way to do this. Has anybody ever seen a factor tree before? Put a yes in the chat if you have. Just wondering if you've seen it. No, okay. So here's how it works. Lewis, you're the first person to respond. Give me 2 random factors of 240. It doesn't matter what they are. Eric has, that's good. If you're getting stuck at all, you can always say, it's an even number, so 2 and 120. Yeah, 4 and 60 works. So that's actually a good start because 4 is a square number. So you could just go ahead and say that's 4 times 60 and then worry about root 60 in the problem. So this is kind of an up in the air sort of way to do it, but it can work this way as well. Okay, so give me 2 factors. What are the 2 factors of 4? So that there's only one option really, 2 and 2. Somebody give me 2 factors of 60. Who is next? You were next in the chat. 4 and 15, very good. 4 and 15. Okay, so 4 again is going to be 2 and 2. Once you've gotten down to a prime number, you can stop. And 2 factors of 15. Well, there's only one option. 3 and 5 is what it's going to be. Thanks, Jamal. Okay, so what I can say from this, I've now got the prime factorization of 240. It's 2 times 2 times 2 times 2 times 3 times 5, or if you like, 2 to the 4 times 3 times 5. Now, we're only using this as a tool to try to reduce 240, so it doesn't really matter which way we go. Somebody else might have said in the beginning, oh, not 4 and 60, let's use 2 and 120, or let's use 8 and 30, I think would be the other option. Lots of options that you could start off. If you wanted, you could even stop at 4, right? Because as we see 4 here, we're kind of thinking, well, there's a square factor. That's one of the things I'm looking for. So I might just say, okay, it's 4 times 60. So it's 2 root 60, and then worry about 60 afterwards. So it's really just up in the air. You can kind of do what you want with this one. But how this kind of factor tree works is if we have 240, we just figured out that 240 is 2 to the 4 times 3 times 5, which is the square root of 2 to the 4 times the square root of 3 times the square root of 5. Okay, 2 to the power of 4 is 16. Whoops. And the square root of 16 is 4. Times root 3 times root 5. So since root 3 and root 5 don't reduce any further, there's no point in having them as separate terms. So we can do this is the square root of 3 times 5, kind of going backwards. So 4 root 15 would be the simplest form of root 240. Now I've kind of gone a long way about this. You could kind of get to 4 root 15 pretty quickly. I've just kind of shown every step here exhaustively. And yeah, maybe if you're good at mental math, you're able to spot that 16 is a factor of 240 immediately. That wasn't something that I noticed, but I guess 16 times 15 is 240. So that's something you might need to do from time to time to get those square factors out. It's called a factor tree. You can just start with the 240 and just start splitting the factors, just going down in kind of in a tree kind of form like that. Somebody spotted 4 by 60. I think Lewis was first, and then 4 was 2 by 2. 60 is 4 by 15. 4 again is 2 by 2. In the end, it was 4 2s in the end, so 2 by 2 by 2 by 2, and 3 by 5. And you can just play with those numbers inside the square root to make it simplified. Kind of a handy way to do it. Just put your thoughts on paper instead of sitting there kind of going, what are the factors? 2, 4, 8 go in and stuff like this. Kind of a nice way to get your thoughts on paper. Any questions here? Yeah, nice little technique. Not something that you kind of have to do to be able to do it, but handy little technique. Whoops. Okay, so some more simplification. Let's say we're looking at minus 5 times root 12 minus the square root of 32. What would I do here? So my first thought as I'm looking at this is that I would like to remove any square factors and see what those kind of base square root terms are and see if there's anything that we can do. So I think we already did root 12, right? It was 4 by 3, so it's going to be 2 root 3. And 32, 2 and 16, thanks Jasmine. 16 times 2. So multiplying out here, minus 5 times 2 is minus 10. Square root of 16 is 4. And there's nowhere else we can go from there. We can't simplify any further. So what I was just watching out for in the final step to see if there was going to be a final step was if they both ended up being root 3 or root 2, then I would have added those terms. I would consider them like terms. Like if we were doing minus 10x minus 4x or something, you would then say it's minus 14x. So, you know what, let's make it work out. Let's add some other terms in just to demonstrate that. So let's say I have plus 7 root 8 minus the square root of 108. Okay. So, okay, we've already done the first two terms here. How about 7 root 8? 8 again is 4 times 2. So it's plus 7 by root 4 times 2. And 108. So hopefully without doing the factor tree, can anybody think of factors of 108 that would work the best? 12 and 9 are 2 factors. I think we can do better. Yeah, we might just go to the factor tree on the side here, but I do see one rather large square number that's a factor. Anyone know what it is? No, 54 isn't a square number. 54 and 2. Like 54 is a factor, and one thing that you might do, you might just go to your factor tree and say 54 by 2, and then you're going to take the 54 and go from there. But it's not a square number. 4 and 27. Is that right? That is right, 4 and 27. 3 and 36, Jasmine and Eric, that's right. That's the number I was looking for. 4 and 27 does also work. But you'll notice that 4 is a square number, 27 is actually 3 cubed, so it's 9 times 3. 9 is also a square number, so it's kind of combining the 4 and the 9 to make 36, another square number. Okay? So, sorry to anybody that hates doing mental math calculations in their head right now. This is probably an awkward one to talk about, but yeah, 3 and 36 is what I was looking for there. If you can find it, the best thing to do is go for the largest square number. And 36 is definitely the biggest one that's a factor here. But if you're not sure, like if let's say we started off with the very first suggestion, 12 and 9, we could just go ahead and say that that's root 12 by root 9, and then we'd realize, oh, okay, root 9 is 3, so that comes out. But root 12, that's 4 times 2, so we can pull out a 2 afterwards. It would still work out. So none of the suggestions are wrong here. It's just that there's a better option to start off with, that's all. So this is the square root of 36 times 3. So to continue this question, to make it a little harder, 7 times, so the square root of 4 will come out as 2, and that is going to be 14 root 2. The square root of 36 is 6, so that leaves you with 6 root 3 here. Okay. Okay, so now the reason I added these extra terms in was because I wanted to just demonstrate one last thing with this. I would look at these two as like terms and these two here as like terms as well and add those up. So minus 10 root 3 minus 6 root 3 is going to be minus 16 root 3, and minus 4 root 3 minus 4 root 2 plus 14 root 2 is 10 root 2. Everyone's okay with that addition? If you're not quite happy with that, what you can kind of do for a second just to see why it works is sort of mentally think of this as minus 10y minus 4x plus 14x minus 6y. So it's kind of like the x is a root 2 and the y is a root 3. And what would you do if you had minus 10y minus 6y? You just say, oh yeah, minus 16y. Same thing, minus 10 root 3 minus 6 root 3 is minus 16 root 3. Likewise with the root 2s. Okay. Any questions here? Okay, it's been almost an hour and a half, so what I'm going to do is take a little break before I continue on with these. So I'm going to say return at, let's take 10 minutes, 11:35. So don't be late back. I want to get right back into it. Continuing with radicals, we also have to do conjugates, functions, domain, and range. So we have a fair bit left to do today, so make sure you're back on time. But yeah, just a little quick break now, okay? I'm going to go grab some water as well. Okay, break time. Hello. We will start again now momentarily. Minoji, yeah, I think so. You should have gotten one from Continuous Learning. Can anybody else confirm that you got it? Who are my usual responders? You did get it, okay. Double check your email again, Minoja. Maybe check your spam as well. Sometimes certain emails send stuff to junk folders and spam and stuff. And make sure that you're checking the same email account that you originally started with. What do you mean in your dashboard, Jamal? Probably would have been an email. I'm not sure because I didn't organize it. That's the administrator's job to organize the sessions. I just teach. But it should have been. What would be up by Monday? The course shell, the other course shell. That exists now. I think should be able to find that. But apart from the course shell, in your emails, you should have got something, maybe an online form to choose Tuesday, Wednesday, or Thursday. And if you didn't choose, I think you're automatically put into one of the sessions. So just check your emails, and if you don't see it in there, email Nicola from. I did that. Okay. You really should have got it though. Yeah, just email Nicola from. It's probably. Oops. Probably that email address. Just to say, I never got the email. Yeah. And for everybody else who did get the email, can you also see the academic coaching course in Beside Math and academic writing and stuff in your Canvas shell? You can see that too? Okay, good. So, excellent. Okay, everybody can see it. So it's been done, and you should have access. So if one of you or one or more of you don't, then maybe some kind of a glitch happened or something else, or you weren't added properly. So just make sure that you're logging in with your same email address. Okay, you can see it. Okay, good. Yeah, just make sure that you're able to see it and attend today if you have to attend today. I don't know which sections you're in, but yeah, just attend your section. Okay, any other questions about this before we go back to math? Go ahead, Lexi.
I was wondering if there's any possibility I could change what class I'm in for the academic coaching, because I'm supposed to be in yours today, but I have to work today and next week, and I didn't realize that there was a choice as to like which one I could choose for the week.
Okay. Yeah, email Nicola as well, and she should be able to change which one you're in. So again, I'm not sure exactly what you guys can see on the coaching course. Like, can you see all three links, or can you just see the link associated for the one you picked?
I can't see Paris's, but I can see yours and Chris's links for the Tuesday and Thursdays.
Okay. Then what I would do is just send an email to Nicola and say, hi, I selected the Tuesday section, but it turns I forgot that I have to work or whatever. And is it okay if I attend Chris's on Thursday? She'll almost certainly say yes.
Okay, thank you.
It'll be sorted. Yeah. I'm guessing that it's whichever one you originally signed up with. Yeah, same for you then, Samira. Do the same thing that I suggested for Lexi and go to a different section. I don't know because I didn't organize or make the form for you to select. I thought that the plan was that there was going to be a form where you could select yourself into. And if you didn't, then you got automatically put in one because we needed to have lists finalized by today. Can anyone confirm if you did get a form to pick which section you wanted? Cynthia?
I was just searching through my email and I found it from Friday, but it was like all the way at the bottom of the email, so I didn't see it.
Oh, you didn't see it. Okay.
Yeah, it was sent on Friday, I think.
Okay. Yeah, so I think if somebody didn't pick their section, then she automatically just put you into a random one and said this is your section. So if you missed it, then yeah, if you didn't see it at the bottom of the email or something, then you got put into one automatically. But I think that is probably closed by now because we're trying to keep like an even spread of you across all three instead of having say me or Chris or Karis, one of us having almost all of you and only being one or two in the last section. So that's why it was kind of evenly spread in the end. So yeah, you probably can't select any more. It's probably closed now. But if there's an issue with the one that you got put into, email Nicola. I have the email address in the chat, and just say, "Hi, I'm sorry I missed the form that you sent. I didn't see it at the bottom of the email. I am actually not good for the day that you put me in for. Can I have this day instead or whatever?" I'm sure she'll shuffle it around somehow. It might mean that somebody else gets plucked out of one of the ones they were put into, but we'll see. Access. So my one is today. You can find the link it's a Google Meet link. You can find it in the course shell, the academic coaching shell. Paris's meet is tomorrow. I guess she'll update her link soon and put it in there. But you can just click the link in the academic coaching course on Canvas. You should see academic coaching in beside math, academic writing, academic success, and I'm guessing academic coaching is in there too. Okay, so I think that's just somewhere that we might post some slides or content or some resources that we use through the term. We might just put it in there so that you all have access to it. It's the same course for all of you, even though you're in different sections. So if you're in my section, if one of you is in my section on a Tuesday and another is in Chris's on a Thursday, you'll still have the same course. You'll be in the same thing that way. Yeah. Go ahead, Samir.
Sir, usually I work all the time for all of those 3 sessions from 2 to 3 o'clock. Those sessions I'm always at the work, so.
They're all from 2 to 3.
No, I see there's 1 to 2, but I leave my house at 1 o'clock to get to the work.
Right.
So.
Which section were you placed in?
Right now I can see yours and Chris.
Well, weren't you sent an email saying that you were supposed to attend mine or Paris's or Chris's? Were you put into one of the classes yet?
No, I don't think so.
Can anybody confirm if you've been told which section you're supposed to go to? In the chat? Franklin, yeah. Okay, so Samir, you should see in your emails, I'm guessing. I'm guessing that you haven't checked your emails thoroughly enough if you haven't seen the instructions or read them carefully enough, but it seems like everybody has been given which section they're supposed to attend. So if you check through your emails and see which section you're supposed to attend, maybe contact that coach and you can go from there. Okay?
All right, I'll do that.
Okay.
Thank you, sir.
No worries. Yeah. Just make sure you're checking your emails very thoroughly and reading everything that's sent. It's always going to be the primary line of communication between you guys and university, whether it's the administration or professor or coach or anything. Always make sure that you're reading your emails thoroughly and carefully and checking it daily, at least daily. so that you don't miss anything that way. If you're not sure, it'll take me a little too much time to find the files right now during class. So if you're not sure what you're supposed to be doing, send me an email right after class. So my coaching section starts at 2 o'clock today. Just send me an email after class and I'll see if I can help then. But right now I really have to move on with the math to make sure that I get enough covered in class so that you can take your quiz on Friday without needing to watch extra videos or whatever, okay? So just send me an email if you're still not sure about something, okay? But make sure that you check your email thoroughly and regularly and, you know, read everything carefully in there. Okay, so back to radicals. Which number are we on? 3. We've done 3 examples so far, so let's call this one 4. Just some more simplification. Let's say we have 2 over x to the 7 square root of it times the square root of x to the 21. Those properties that I highlighted from the textbook earlier about the multiplication and the division, those work backwards and forwards, and they can also be applied here. So one thing I'm noticing is that I have a root 2 over root x to the 7 here, and here's a root x to the 21 still there. In trying to simplify this, I can note that this is like root x to the 21 over 1. And when multiplying two rational things, I multiply top by top and bottom by bottom. Root x to the 7 times 1 is just going to be root x to the 7. And where I go from here, you know, you can kind of choose your approach. You can try to take out the square factors, but I think what actually might be nicer is to make a cancellation first. So my instinct for this kind of one is to say, okay, that 21, I can rewrite this as x to the 7 times x to the 14. And the reason I wanted to do that is because in my next step, I can say that this is root x to the 7 times root x to the 14. Oh, sorry, that's the wrong thing I've written down. Root x to the 14. This is root x to the 7. And now I see a common factor on top and on bottom. So that and that will cancel. I have a root 2 times root x to the 14. Anybody know how what I'm going to do with this root x to the 14? So I can rewrite it another way. Any ideas in the chat? I'll keep going, actually. I'm a little tired for time now. So I can rewrite this as x to the 7 squared, like that. Let me just make sure this is written clearly. That square root is extending over everything. Now, the square root and the power of 2 kind of reverse one another. They'll sort of cancel one another. And what I can say then is that this is root 2 times x to the 7. You can kind of think of that square root and the power of 2 cancelling. You square something and then take the square root, you're back to where you started. Another example like this one. Yeah, it's kind of similar. Not so much with the higher numbers inside the square roots. Did you have a question about this along the way? Miss a little bit of it or something? Feel free to unmute if it's... Okay, so I'll run through it one more time. So we started off with root 2 over x to the 7 times root x to the 21. So my first thought was that I don't like having this square root in underneath the this fraction symbol underneath the square root. So we split it into that. We said it's root 2 over root x to the 7. That was multiplying by root x to the 21. So you can now treat this as like multiplication of rational expressions if you treat the root x to the 21 as root x to the 21 over 1. Okay? So multiplying top by top and bottom by bottom, you have root 2 by root x 21. That's the top. The bottom is root x to the 7 times 1, which is just root x to the 7. And from here, I'm looking for ways that I might be able to make cancellations and simplify and reduce it somehow. So what I'm noticing is that if you have x to the 21 like this, that's the same as x to the 7 times x to the 14. I mean, it's also the same as x to the 6 times x to the 15, x to the 10, x to the 11. I can split that up anyway. It's kind of like if you go in the reverse order, you would add the two powers. But this is the one I want. Not these two. Because that actually helps me get a cancellation later. Because when I use x to the 7 over x to the 14, you can split the square root over the two of those and then make the cancellation. So you can split the square root over the two and then make the cancellation here and here. And that just helps a little bit. It reduces the problem a little bit, gets rid of the denominator. Okay, good from there. No problem. Anytime. Always feel free to ask a question. I like questions. It doesn't matter if we go over time. I can make a video and I can post it for before the quiz on Friday. So don't be afraid to ask a question just because we get a little bit delayed. Anytime. That was question 4. So let's go for 5. Another one here I'm looking at is, let's say we're trying to simplify 3x times root x over y times root 4x over y. Okay, lots of different approaches here. In particular, I'm seeing 2 ways that I might begin. Any thoughts on how you might start this one off in the simplification? I'm torn between 2 different things to start off with. So it's not always one thing that's right. You can get there with you can get to the right answer with different methods sometimes. I guess based on the rules that we had, no fractions under square roots. First thing I'm seeing is that I might just exercise that property and treat that as root x over root y. Just put in some multiplication symbols here. And this is root 4x over root y. I'm going a slightly longer way about it. I can see a slightly quicker way, but this would be the most natural way to start, I think. What I'm noticing next is that in one of those square roots, I have a square factor. 4 is 2 squared. So I can extract that 4, and I can have 3x times root x over root y, root 4 by root x over root y like this. Now the reason I wanted to do this is because this square root of 4 here is 2. So I'm going to take the square root of 4 and say that that's 2 and bring that 2 to the front and multiply it by the 3. So I'm going to have 6x times root x over root y times root x over root y. So this is 6x. If I multiply top by top and bottom by bottom over here, I have root x by root x, which is going to be root x squared. I have root y by root y, which is going to be root y squared. So this is 6x times x over y, which is 6x squared over y. Scroll down a little bit. Any questions here? Everyone feel pretty good about this one too? Now, a way that I could have got there a little quicker, where did the exponent come from? Oh yeah, so this is just, no, if you have a different way that works, we want to distribute to the 3x. Okay, I'll get to those one by one. So first thing was, where did the exponent come from? This here, root x times root x. Let's say you had 2 times 2. That would be the same as 2 squared, right? Root x by root x is root x squared. Okay. Likewise for the root y. Is that cleared up, Evan? Okay, Maximus, I'll go over it again. I'm just going to go through the questions first because they're a little more specific. Do I have to follow your method of solving? No, if you get to the right answer using a slightly different way, if you get to the same answer, the chances are really high that you haven't made a mistake and what you're doing is okay too. I was also thinking of extracting that 4 to begin with, and then having root x over y times root x over y, which is just x over y. It would have gotten there a little quicker, so if that's what you did, that would be totally fine too. Why did the 2 only distribute to the 3x? So that's just that's like a property of multiplication, I guess. Let me see. So let's say I have, again, I'm going to go back to numbers. Let's say I have a 4, and in here I have a 5 by a 6, right? So you know what the answer would be, right? It would be 5 by 6 is 30, and 4 by 30 is 120. So we're satisfied with that. But if I was to distribute the 4 twice, like this, 4 by 5 times 4 by 6, that would be 20 times 24, which is 480 or something way bigger, right? So you only distribute, in multiplication, you only multiply a number by one of the factors. And it can be any one of the factors. It doesn't have to just be the 5, for example. It could be the 6 either. So that would not be the way to do it. Do you follow? Find this one little awkward answers, Araya. Does that make sense? Okay, so just going back a little bit, another way to look at it would be, I could have 4 times 5 times 6, which is 20 times 6, which is 120. Or I could have 5 multiplied by 4 times 6, which is 5 by 24, which is also 120. So the 4 can multiply to 5, the 4 can multiply to 6, but what you won't have is 4 times 5 multiplied by 4 times 6. Because what that really is, you've created an extra 4. That's like 4 squared times 5 times 6. Whoops. Sorry, I wrote the wrong thing. So you're creating an extra 4, and you're gonna have too many. Your number's gonna be too high in the end. Okay. Yeah, it's like a property of multiplication that the number only multiplies on one of the factors, not all of them. Just gonna take this away here. So just going back then, so now that you're kind of satisfied with that, the reason I multiplied it to the front is because we tend to prefer things that look like 5x or 6x squared y or 7x y z, whatever it might be. Just, I suppose it's a habit or a convention that if I see x y squared by 5 by z, I'm inclined to make that 5xy squared z by bringing the number to the front. Because the order of multiplication doesn't matter. It actually doesn't matter at all. But it's just the thing that we do is we generally put the numbers in front and the variables after when we're listing the things multiplying, listing the factors. So when I have like let's say we have a 5x squared by 2 by y, I'm inclined to say, okay, 5 times 2 is 10, x squared y. Okay, no problem. So it's just kind of it's as much a convention thing as anything else. It can be confusing a bit, but okay. That was all of those style of examples I have for you and simplifying some of the square roots. It's about getting rid of the squares from under fractions, trying to find things that cancel or simplify or manipulations and stuff. It's really just practice, practice, practice. And one other thing to note, actually, I'm sure you remember this, but if you're looking at the nth root of x to the m, sometimes you see them written in this way. This would be x to the power of m over n. So for example, some other examples that you might just see, maybe if you're on the internet looking stuff up or you're looking up stuff in different textbooks. The square root of x is the same thing as x to the power of a half. The cubed root of x is the same thing as x to the power of a third. The ninth root of x would be x to the power of 1/9. This should look familiar. And also if you have, say, x to the 7, the 11th root of it, this would be x to the 7 over 11, like that. Okay. So that's just a quick note about some of the different notations that you see. Square roots are also exponents in a way. They're fraction exponents. On the exam, would we be able to create a formula sheet? What do you mean by create a formula sheet? Like, you mean, oh, you mean like bring in a formula sheet to a test? These should all be memorized. These rules you should know them well. You shouldn't be using formula sheets for these. Yeah, going again. This course is about preparing for calculus and for university math. You're almost never allowed formula sheets or aids in university exams, so it doesn't really make sense to have you beginning to rely on them here now, using formula sheets as a crutch. For me, it's not as much about memorization. It's about I practice it so much that I don't forget it. I guess maybe a little bit of memorization too, but if you do enough practice and enough problems, you're often not kind of going to your brain going, okay, that formula sheet that I memorized, what's one of the rules that I have to do? It's more that you've done it so much now that you see the patterns and you just know what to do, kind of. So if you practice a lot, you should remember a lot of these rules anyway. But yeah, maybe you'd make some kind of a formula sheet yourself and run over it every so often just to make sure that you remember them. Yeah, no formula sheets or other aids in the tests here. The quizzes aren't really supervised, and they're multiple choice. You can do what you want with those, but the assignments, I guess you're going to be using your text for that. But midterm and final are to be done independently of any notes or anything. Okay. Okay, so there's one more thing I wanted to look at in radical expressions, and again, you should be keeping a close eye on the textbook as well, just to get a little more background that I'm providing in class here, because I kind of have things written a lot more detailed in the book. So you should be keeping an eye on that while you're working through things and your practice and everything. But moving on to conjugates. So let me just see, does anybody know what conjugates are for? So what is, for example, if somebody can write in the chat, what is the conjugate of, for example, 1 plus root 2? If you know what a conjugate is, you might be able to, okay, a square root symbol might be difficult to write in the chat, but just write the word root or something, R-O-O-T. Know what the conjugate of 1 plus root 2 is? Do we know what conjugates are? Can I get some yeses or nos? Oh, that's surprising. Okay, well, I'll go over this a little more slowly then. So, conjugate. Okay. Jamal, you're exactly right. The plus will become a minus in this case. To get the conjugate, and it's not always plus to minus. You are right. We are changing the plus to a minus, but think of it as changing the middle sign. It could go from minus to plus in certain cases too. So change the middle sign. That's what you're going to do when you want to get the conjugate of something, okay? Now, this is going to loop back to radicals very soon. We're not going off on a crazy tangent here. So for this reason, the conjugate of 1 plus root 2, for example, is 1 minus root 2. Let's say we have 2 minus root 3, then it would be 2 plus root 3. If it's root 7 minus 1, you can call it root 7 plus 1. So the nicest way to do it is to think of changing the middle sign. Now, the reason that we're talking about this the reason that I'm mentioning it is that conjugates are used to simplify certain radical expressions. So remember, we talked about removing square numbers from inside square roots. We talked about when there's a fraction inside the square root. And we also talked about when there's a square root in the denominator. And so far, I think the example that I had was, oh, what do you do if you have 1 over root 5? Well, you can multiply above and below by root 5. Then you have root 5 over 5. Ta-da, easy peasy. We have taken the square root out of the denominator, and now it's in the numerator, okay? But sometimes the problem is not quite that easy. So for example, let's say I want to simplify 4 over 1 plus root 2. Okay, so what I'm seeing here is that I have a square root in the denominator. I don't have any square factors inside square roots. I don't have fractions underneath the square root symbols, but I do have a square root in the denominator. Now, your first thought might have been, oh, well, I remember what to do. I'm just going to multiply on top and on bottom by square root of 2. So let's see what happens if we do that. 4 over 1 plus root 2. If I multiply on top and on bottom by root 2, what do I get? I get 4 root 2. Here's a problem. I have to multiply both the root 2 by both of these terms. So I'm going to get root 2 plus root 2 times root 2. So the second term sorts itself out because that's equal to 2. But now I have root 2 plus 2. I haven't solved my problem because I still have a square root of 2 here. So I haven't rationalized it. And if I multiply it by root 2 over root 2 again, then I'll just move it back to this term. So I won't actually solve it by doing this. This won't work. But conjugates help. Let's see what I mean now. So this is the solution. Not what I just tried. What we had was 4 over 1 plus root 2. When you see something like this, what you're actually supposed to do is multiply above and below by 1 minus root 2. You multiply above and below by the conjugate. And this will actually work out. So let's see what happens when we do this. We're going to have 1 times 1, 1 times negative root 2, root 2 times 1, root 2 times negative root 2. So on top we have 4 times 1 minus 4 times root 2. And on the bottom we have 1 minus root 2 plus root 2 minus root 2 times root 2. Root 2's will cancel. This here is equal to 2. So what we have is 4 minus 4 root 2 divided by 1 minus 2. Now it's worked, right? I don't see a square root in the denominator anymore. The square root terms, they cancelled out right here. And the other square roots that were left, they multiplied by one another, so the square roots kind of got cancelled away. It's like root 2 squared. So the power of 2 and the root got cancelled. So now we have 4 minus 4 root 2 divided by negative 1, which is equal to minus 4 plus 4 root 2. Okay. Any questions here? This is a little new. I'm expecting some uncertainty. Okay. Okay, so there is a kind of a shortcut way to think of this, or a reason for why this works, right? Let's say we have I'm going to do another example and we'll talk about it then. So, okay, that was an example with numbers. Another way that you might see this written would be to rationalize the denominator or the numerator depending on the situation. Rationalize the denominator of, let's say we have x squared minus 1 over root x plus 1 minus root x squared plus 1. And simplify fully. Okay, so this is actually, these types of questions are really geared towards certain calculus problems that you're going to come across next semester, assuming that you pass and everything. So, has anybody seen limits in high school yet? I assume you've seen some limits by now. Get some yeses in the chat. Okay. So, what you might notice about this problem is if I sub in x equals 1 into this, what does this look like? Subbing in x equals 1 into the numerator, I have 1 squared minus 1 is 0 on top. And if I sub x equals 1 into the bottom, the first term is a root 2. Second term is a root 2, so I have root 2 minus root 2, I have 0 on the bottom. So for x equal to 1, this problem looks like 0 over 0, and that's not defined. Now it might be just undefined, or it might actually have a limit if you take the limit and do some work with it. Now, so a problem that you might see in calculus next semester is find the limit of this expression as x goes to 0. As x goes to 1. Because if you sub in into a calculator, for example, 1.001 and then see what it is, and 0.9999 like that, those might be very close to the same number, and there might just be like a little hole on the graph saying what it actually is when x equals 1. But with some conjugates, which we just learned about, we might be able to work with this and figure out what that number would be exactly, not just by subbing in numbers close to 1 and guessing. So that's why we're touching on conjugates in the radical expressions here, because it's something that you're going to have to do in calculus. So yeah, this course is designed to be as helpful for calculus problems as possible. It covers the high school material, but really with a view to university calculus. So this is the kind of thing we're going to see. Some of the questions are going to look weird at times, but it's because they're very much geared towards helping with calculus problems. Okay, so rationalize the denominator and simplify as much as possible. Okay, so here we're going to take our x squared minus 1 divided by root x plus 1 minus root x squared plus 1. And to rationalize the denominator, we multiply on top and on bottom by the conjugate of the denominator. So, as we just discussed, to multiply by the conjugate, you have to change the middle sign and multiply top and bottom. So which sign do you think I want to change? Number 1, number 2, or number 3? Just drop it in the chat for me. Good, everyone's saying 2. Yeah, good instincts. 2 is the one you want to change. So we're gonna change that middle sign and multiply top and bottom. So root x plus 1 plus root x squared plus 1 divided by root x plus 1 plus root x squared plus 1. Okay, now, how do you know when to multiply by the conjugate? Because I want to rationalize the denominator. The reason I'm multiplying by the conjugate is because, so rationalize the denominator, if you kind of break down the wording there, that means, I guess I could go all the way back to rational numbers, but a rational number is one that can be written as a fraction. Square roots of numbers can't be written as fractions. So square root 2, square root 3, those are not rational numbers. So when we say rationalize the denominator, it means get rid of the square roots, because for certain values of x, that denominator won't be rational. So when I see rationalize the denominator, I interpret that as get rid of the square roots from the denominator. And the method to do that is to use conjugates. So when to use conjugates? When you see rationalize the denominator, rationalize the numerator, depending on what it says, then I'm going to use the conjugate. Okay. Now, the reason that this works is because, and this is a bit of a shortcut, like this looks like it's going to be hell of a multiplication. Doing first, outside, inside, and last, that FOIL method on all those terms, looks like it's going to get kind of ugly. But instead of doing that, what I'll note is that in multiplying by the conjugate, do you remember your difference of squares formula? You had a squared minus b squared. It was a plus b. Actually, let me just rewrite the order a tiny bit. A minus b times a plus b. In here, I had an a minus a b, right? In multiplying by the conjugate, I've essentially multiplied by the a plus b. In this case, a is root x plus 1, b is root x squared plus 1. I have created that. So I know that the answer that I'm going to get from my comfort with the factoring techniques and formulas is going to be a squared minus b squared. So instead of doing all that multiplication out, what I'm going to do is, okay, the numerator is going to stay the same. Let me just write that out. Instead of doing all the multiplication, the first, outside, inside, last, I'm just going to take a quick shortcut here and say this is root x plus 1 squared. Sorry, it's a minus sign. Minus root x squared plus 1. This here is like my a squared minus b squared. Okay, I don't know why I wrote that so far away. Does that make sense? Kind of a shortcut where I'm avoiding all the multiplication. Does that work? Just put a yes for me in the chat if you follow. Oh, I'm missing a square, haven't I? I wonder, nobody's sure. Yes, yes, Evan, it should have a square as well. Thank you, yeah, I missed it. Okay, good. So that's kind of a shortcut. It just avoided all that multiplication. The square root and the power of 2, the square root and the power of 2, those are all going to cancel away. And on top I have root x squared minus 1, root x plus 1, plus root x squared plus 1 divided by, here I have x plus 1 minus x squared minus 1 in the bottom. So that's just distributing the minus sign through the brackets. Okay. 1 and minus 1 cancel. And here's where again, I want to be rock solid with my factoring so that I'm not spending too much energy worrying about this. I'm noticing that on the bottom here, I have x minus x squared. So I can take out negative x if I want and be left with x minus 1. On top, I had x squared minus 1, so it's x plus 1 times x minus 1. Everyone's okay with that step as well? Just some factoring. You know what, maybe on the side I'm just going to demonstrate the bottom bit, because that one I did do something a little. So it was x minus x squared. All I did was change the order and then common term factor out minus x. And I did this because looking ahead, I saw that on the top I would have a factor of x minus 1. So I wanted the factor of x minus 1 on the bottom. Okay, so I'm going to rewind for a second. Going back up here, remember I was talking about why we do this and what happens at x equals 1. At x equals 1, this expression up here, it looked like 0 over 0, which is undefined. But we actually have now made it defined by doing some manipulations here to see what it looks like, see what the limit is, if you remember the terminology. So now I can actually, because you notice that I've cancelled the x minus 1 and the x minus 1. That was what was causing the 0 over 0, that x minus 1. Because if you look, if you plug in 1 in here, you have 1 minus 1 on top, 1 minus 1 on the bottom. After using the conjugate and doing some factoring, we're able to get rid of that. And now on top, if you plug in on top and on the bottom, if you plug in 1, you don't get 0 over 0 anymore. So this conjugate technique, this factoring, this is all in the background. Because in calculus, when you do it, what you're going to be doing is a limit problem. The question will look something like, what is the limit as x approaches 1 of all this? And you go, as I put in x equals 1, it's 0 over 0. Well, that's okay. I remember from Jason's class back in the summer, we did this whole thing with conjugates. And we multiplied above and below, we factored, we cancelled. And now I'm going to have my limit in here. Limit as x goes to 1. I can now plug it in and I can solve. So if you remember your limits, that's something that's going to be coming soon. But we're not talking about limits in this course. We're just talking about radical expressions and reminding about all that. So in the end, what we have is x plus 1 times root x plus 1 plus root x squared plus 1, all divided by negative x. That would be your final answer. So for this question, what we were actually asked to do was rationalize the denominator. Done. We got rid of the square roots. Simplify as much as possible. Done. We managed to cancel the factor. And that's as far as we can go here. We can't make any more cancellations. Any questions here? Okay. Maybe tell me as well, put a yes in the chat if you've seen, so I'm just thinking about the rest of the class. Have you seen domain and range before? Me, yes or no? Awesome, okay. So I might need to spend so much time on domain and range then, which means I should be able to do one more example of this. I'm guessing you'd prefer to see one more example like this over a little extra time on domain and range today? Okay. Sure, we'll do one more of these and then we'll move on to the functions for the last little bit of class. So another example with conjugates. This time it has a slightly different instruction. And you have to read carefully and see what you're being asked to do. This time it's rationalize the numerator of 2 times root x plus 6 minus 6 divided by x minus 3. And simplify. So the same instruction as last time, except this time we're rationalizing the numerator. Now, I understand this kind of goes against what I was talking about from radical expressions, where you're saying, wait, you want me to put a square root into the denominator now, so get it out of the numerator and into the denominator? That's not really, so we're sort of stepping away from simplifying radical expressions now, and this is just a random instruction that we want to rationalize the numerator. But the approach is going to look the same. We're going to use the conjugate. And the reason that we want to rationalize the numerator is because notice that if you put in 3, so again, this is like thinking about calculus. A future question might look like this. The limit as x goes to 3, find the limit as x goes to 3. And if you put that in, you have the square root of 9 on top, which is 3. 2 times 3 is 6. 6 minus 6 is 0. So you have 0 on top. 3 minus 3 on the bottom is 0 on the bottom, and it doesn't work. So you can't find the limit from subbing in. So what we're going to be doing is using, again, that radical expression technique to make it work. But of course, for this course, all we're talking about is, I'm just going to tell you, rationalize this, simplify that. I won't be mentioning limits. That'll come next semester. We're just working on the kind of the mechanics of the techniques here. So this one, we're not simplifying the radical expression. We're actually moving away from the kind of form that I mentioned that we like, but just to make a future problem kind of work out. Okay, so here the conjugate is going to be, as you might have expected, 2 root x plus 6 plus 6 over here. And it has to be the same on top as on the bottom. Okay. So when we multiply these together, we have 2 root x plus 6 minus 6. 2 root x plus 6 plus 6 on top. And x minus 3. 2 root x plus 6 plus 6. Okay, so again, I'm going to take that shortcut. I have what looks like an a minus a b times an a plus a b. You know what happens when we multiply a minus b times a plus b? We covered this not yesterday, last week in difference of squares formula. It's a squared minus b squared. So it's 2 root x plus 6 squared minus our b squared, which my b kind of looks like a 6, which is convenient, but I'll try to make it look more like a 6. So this is your a squared minus b squared. And your denominator is going to stay the same right now. 2 root x plus 6 plus 6. Okay, so let's get to simplifying and see if we can make any cancellations or something here. So squaring out this first term, what we get is 4 times x plus 6. Don't forget that when you have, oh, my 6's look terrible. I should have wrote 6 better. When you have two things multiplying inside a bracket, like this and this here, the power of 2 applies to both of them. It's like, it comes from this property that's like ab squared is equal to a squared b squared, like that. So that's why it's 2 squared times root x plus 6 squared. 6 squared is 36. The denominator is going to stay the same for now. So now multiplying out, let's see what we get. We have 4x plus 24 minus 36. X minus 3 times 2 root x plus 6 plus 6. So this is going to be 4x minus 12 by x minus 3 times 2 root x plus 6 plus 6. And factoring the 4 out of the top, you're going to get x minus 3. Okay, I think I went through those steps kind of quickly. Any questions here? I'm going to pause and see if anyone has a question really quick. Okay, if we're doing fine, then I'll just go ahead and finish this one off. Again, if you remember at the start of the question, I was mentioning what happens at x equals 3 might be the problem for calculus. Well, that's no longer a problem because our 0 over 0 is going to go away. And now, my 6s, I hate my 6s. There we go. That would be your final answer. Yeah, it doesn't look like it's in a simplified form, and it's not. It's we have a square root in the denominator, but the instruction for this question was to rationalize the numerator. We don't really care about the denominator right now. Just depends on the question. Okay, where did the 4x minus 12? That was 24 minus 36 is minus 12. Was it before that, or does that answer your question? You clear on that one? Okay. I'll read the question. Oh, okay. Okay, so yeah, there's a whole bunch of those for you to practice as well. So going down, we had the addition and subtraction of radicals. Conjugates is here in the book as well. Kind of another re-explanation of that sort of difference of squares shortcut that I keep taking. This was the first problem we did. That was the second problem. Find the solution here again. Lots and lots of exercises here to try. The conjugate ones kind of start from question 11 here. They go all the way down to 18. But for 19 and 20, those ones are to rationalize the numerator. And that's going to look really weird with the h in there. But it's going to look very, very similar to something that you're going to cover in a few months in calculus. I know that you cover a little bit of calculus in high school. Do you do the definition? The limit definition? Limit as h goes to 0 of f of x plus h minus f of x over h. Do you cover that definition in high school? You do. Some do and some don't. Yeah, depending on where you were, what you've seen, you may or may not have seen that. But number 19 and 20 might look very familiar to some of you from just seeing that sort of expression in there. You're just missing the limit terminology, really. So make sure you're practicing those. Right now, we're going to move on to functions. So it should be back to something that you're quite comfortable with now. Like we all kind of have a sense for what a function is, right? A function might be something that if I plug in a number, I get a different number. That might be your understanding of it. So, I mean, everybody's familiar with x squared. So x squared is a function that turns 2 into 4, 3 into 9, minus 10 into 100, 5 into 25. So let me just take you back on a little walk back through memory lane, I suppose, and see where a function comes from. It starts off with the definition of a relation. A relation between two sets is a collection of ordered pairs containing one object from each set. Now, depending on what the sets are. They can be anything at this point. A relation doesn't have to be about numbers or whatever. Let's say there's names and ages. Names is going to be the first set and ages is going to be the second. And the relation is the collection of ordered pairs where names come first and age comes second. Jason 29, Kevin 32, Laura 17, Kevin 24, whatever it might be. A name and an age in order in a pair. One you might be more used to seeing, x and x squared, for example. 1 and 1, because x is 1, x squared is 1. 4 and 16, if x is 4, x squared is 16. This is one where there's a rule applied to it. That if the first set is x, then the second set, the pair that goes with it, is the square of that number. So this is going to feel kind of familiar. The set of first components of a relation like this is the domain, and the set of the second components is the range. So for example, up there in the first option there, names was the domain and ages was the range. In the second example, x was the domain and x squared was the range. So that's your first kind of thought about what domain and range are. We're not really going to talk about relations very much though. We're going to move right on to functions. And a function is a relation with the rule that one and only one range element exists for a given domain element. So in another language, it means that a function, for example, if you're used to thinking about x and x squared, you can't have 4, for example, the domain element 4 having a range element 16 and a range element 17. Because there's only one thing that happens to 4. It's a rule that says you take 4 and you square it. You don't take 4 and you square it, or maybe you just make it 17 as well. So it's a specific, the range element is specific to the domain element. Only one range element for any given domain element. Okay? That's what makes a relation a function. And that's a rule that makes functions functions. It's how they work. So for the names and ages on the left up there, those relations, do they make a function? No, because for example, you can have people named Kevin, 2 people named Kevin up there. One of them is 32 and one of them is 24. So the name Kevin can have 2 possible range elements. There can be different people named Kevin that have 2 different ages. You have Kevin and 32, Kevin and 24. For the same range element Kevin, domain element Kevin, you have different range elements. That means it can't be a function. Okay? But going to x and x squared, I mean, you've heard the x squared called a function hundreds of times in school by now, so you know that it is a function. But yeah, that is a function because, for example, for the domain element 6, there's only one possibility. 6 squared is 36 and nothing else. You can't have 6 being 36 and also 71 or something. Only 36. Now, there's one possible little thing that might just be making you go, wait a second though, there's something weird about x squared, is that 16 appears twice. So you have a range element with 2 domain elements. That's okay. You just can't have a domain element with 2 range elements that apply. Okay? So 4 goes to 16, -4 also goes to 16. That doesn't break the rule of a function because 4 only goes to one place and -4 only goes to one place. They both go to 16, but it's not like you have 4 going to 16 and 4 also going to 17. That's where the problem might be. Okay? So, moving on then. This is just an example, really a reminder about domain and range. The domain is going to be the set of first elements and the range is the set of second elements. So I'm going to just breeze past that one a little bit. And we're going to continue talking about functions. So you should read through this in your own time and make sure that you're comfortable with the ideas. I'm just going to breeze through it a little bit here because I want to focus on the important stuff. Okay, functions can be represented in lots of different ways. Verbally, numerically, algebraically, and graphically are some of the ways that I've mentioned here. So, for example, I can describe a function to you by saying, any number you give me, square it, multiply it by itself. Or any number you give me, add 5 to it. I'm describing a function to you so that you know how to get your new number given the old number. Numerically, you could just list all the different ordered pairs. Now that might go on forever, but let's say the rule is to add 1. Then I could describe it by listing all the ordered pairs. 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, like this. Not the best way to do it, but another way that you might describe a function. It's what we were doing back here, actually. Here there was a set of, if you notice this here, this is I think it's not a function, right? Oh, it does define a function in this question. So there was a function described numerically where I just give you all the ordered pairs. Not the most convenient way to do it, but possible to. Algebraically is the one you're going to see the most and the one you have seen the most, I'm sure. F of x equals x squared, y equals x squared, y equals 2x plus 1, y equals x cubed plus 3x minus 2. Those are all just functions given algebraically. You might also see a graph and you have to decide is that a function or not. So here's one where you can see that 1 and 1 is going to be a domain and a range element. 2 and 4 is going to be a domain and range element. You can read it that way. Graphically is possible too. So we're mostly going to see algebraic functions, but just before we move on from the other types, has anyone seen the vertical line test before? I get a yes if you've seen it. Perfect. Okay. So this will just be a reminder then. If you're looking at the graph of a function, if you're looking at a graph and you're trying to determine is that a function or not, all you have to do is try to imagine, can I draw a vertical line on it that will only, I'm phrasing this poorly. Is it true that every possible vertical line I could draw on the graph will only intersect the graph once? If the answer is yes, then it's a function. If the answer is no, then it's not a function. For example, I'm looking at this here. Vertical line, vertical line, vertical line, vertical line. Wherever I draw a vertical line, it only intersects once. So it passes the vertical line test, meaning that it is a function. Over here, I might think vertical line, it seems to be passing, but there is a place where I can draw a vertical line that cuts the curve more than once. This one fails the vertical line test. So that curve that's drawn on the right does not describe a function. So if you see a graph of something and you're thinking, does this work? Then you can apply the vertical line test and see if every possible vertical line I draw, if all those lines will only cut the curve once, then you're okay, then it's a function. But if I can find even one vertical line somewhere that cuts it more than once, not a function anymore. Okay. So here's some examples to think about for the vertical line test. Easy enough, but just a quick reminder. You can tackle those in your own time as well. And moving swiftly on to domain and range. I have to talk about interval notation first as well. Okay. Maybe I will have to put up a video about domain and range after. Okay, so can I get some yeses in the chat if you're familiar with interval notation? Awesome. Okay. Is anybody not? Can you put a no if you're not, if you haven't seen this notation before? No. Okay. So one, or at least one. Some people haven't seen interval notation before. Okay. Well, it's summarized pretty quickly here. Say you're looking at the interval 2, 7. It's been a while. Yeah, we'll recap it quickly here. If you're looking at the interval 2, 7. If you use those brackets, those square brackets with the corners, what you're describing is every number between 2 and 7, but including the two endpoints, including 2 and 7. While if I use the soft brackets, the ones directly below, I'm talking about every number between 2 and 7, but not including the endpoints, 2 and 7. So, for example, is 3 in the set? Yes. Is 4 in the set for, I'm looking at this one here, right? Is 3 is in the set, 4 is in the set, 5 is in the set, 6 is in the set. 6.9999999999999 forever. Okay, not forever, it stops somewhere. 6 point tons and tons of 9s, that is in the set. 7 is not. So when I say to you all the numbers from 2 to 7, I mean everything in between except 2 and 7. Okay. Likewise, you can mix and match the brackets depending on your needs to describe a set. If I use what I'm calling a hard bracket on the left and a soft bracket on the right, maybe I should write this in here actually. I tend to refer to these as hard brackets. These ones here as soft brackets. You'll also see these being called closed interval and open interval as well. So you might hear me call them closed brackets or open brackets as well. So either one of those works for naming the notation, but you can use a hard bracket on one side and a soft bracket on the other if you want. For example, in this one here, what I'm trying to if I write that down, what I'm trying to communicate is that all the numbers between 2 and 7, including 2, not including 7. And in the second one there, all the numbers between 2 and 7, not including 2, including 7. Okay, this is the notation that I'm going to want you to use for this course when you're giving me the domain or the range of a function, when we do inequalities, when we do all kinds of stuff. If you're trying to describe a set of numbers, I wanted to use this kind of notation. It's the most convenient and easiest way to get it across. If you want to describe two different sections, say you want to do all the numbers from -5 to 0 and all the ones from 10 to 20, you'll use your intervals appropriately, but you'll use a union between them. Okay? So the union symbol. So all real numbers, if you want to say every number works, you use -infinity to infinity. And the convention is that you always use those soft brackets or open intervals, open brackets when you're talking about, when you have infinity. You never put a hard bracket beside an infinity. All positive numbers can be 0 to infinity. You're going to want to use an open bracket because 0 isn't really a positive or a negative number. It's just kind of nothing, right? So all positive numbers, 0 to infinity with a soft bracket. If you're trying to say all non-negative numbers where 0 is possible, then you're going to use the hard bracket around 0. And the union notation I just mentioned as well. If you want to describe things that are kind of separate, but they're all part of the answer, you'll use the union symbol. Are there any questions about this? Are you comfortable enough? Most people have seen this before, so if you haven't seen it before, feel free to ask a question, or if you don't want to ask it to the class, feel free to email me anytime and I can answer any math questions too. Okay, so finding domain and range. Maybe we do have time to cover this. You said you've seen this before too. So can anybody tell me what's the domain of the function x squared before I move on? Feel free to unmute if it's awkward to write. Infinity. Yeah, you have the right idea. But remember, if you're thinking about like intervals, it's going to be a whole range of numbers. So when you say infinity, what comes into my head is kind of one thing. You just mean infinity is the thing. All numbers, yeah, any number you want. That's correct. You can square. You can take any number you want and square it. X element of real. Okay, I see. So you're you can write it as x in the reals like that. There you go, Evan. That's exactly what I'm looking for. -infinity to infinity. This is the notation that I want you to use going forward. So -infinity to infinity. Because the question is there any number that I can't just square it? Because that's what you mean by domain. Is there any number that is not allowed into the function? No, I can take any number. I can square 0, I can square -10, I can square -100,000,000.2, I can square 50. There's no number that doesn't work. So my domain is going to be -infinity to infinity. What's my range though? Someone pop the range in the chat or unmute if you want to say it. So another way again to think of domain and range. Domain is all the possible input. Range can be all the possible output. Can I get anything out of it? Evan has it, exactly. And careful, Stephen, it'll be a hard bracket on the 0 because 0 is a possible answer that I can get. Because if I plug in 0 into the function, 0 is what I get out. So I want to indicate that I can have 0 in there. So this would be the domain. I don't know why I'm writing on this. I probably have it written in the textbook. Yeah, here we go. So -infinity to infinity is the domain, and 0 to infinity would be the range. Okay, very good. You can also think about domain and range just when looking at a graph. This is covered too, but so the domain is all the possible numbers that you can put into the function. So based on where the graph starts and ends, this number here, if you look carefully, it's -2.649. And where it stops is at 2. So the domain is -2.649 to 2. I want to use hard brackets here because if you'll notice in the graph, I've used kind of filled in dots to include that the point is on the curve as well. It would be like a hollow dot with a circle if I was trying to say that it wasn't. And what is the range? So the range, you're looking for the lowest y value and the highest y value. The furthest down that curve gets is down here. So going across to the y-axis, that's at 0. The highest it gets is up here. And you can see from what's written there, that's 2.77. So 0 to 2.77 is the range for this one. Okay. Okay, so I'm going to run through an example or two here now. See how far we get. Any questions so far? Okay, we're mostly going to cover domain because range is actually quite hard to find sometimes. Unless the problem is kind of easy. Find the domain of the following. Okay, let's say I have the square root of x minus 4. So, does anybody know what that would be if you can pop it into the chat? You can think of it as a mixture of, what numbers are allowed into the function is going to be the domain. If you like, you can think what's not allowed in the function, because that's what I'm going to try and rule out of the domain. So there's a few ways you can approach it depending on how you prefer. For example, can't be +4. No, it could actually be +4, but you're onto something. If I put 4 in there, I would have 4 minus 4, which is 0, and the square root of 0 is 0. So that's a number that works in the function. I'm allowed to use it. But you're onto something though. +4 is a key number here. Because let's say I do 3.999999999. Then if I plug that in, that number, 3.99 minus 4, that's negative. And I can't take the square root of a negative number. So 3.999 is not in the domain. 3 is not in the domain, 2 is not in the domain, 1 is not in the domain, 0 is not, -10 is not. Yes, it has to be anything above 4. 4 to infinity, exactly. Okay, so Stephen has it there, the answer is in the chat. So what I'm going to do is talk through the more mathematical way to reason it out, then, because me sitting here going 3.999 is not really the best way to approach it. But what you can say to these square root problems is something like, we require x minus 4 to be greater than or equal to 0. It's allowed to be 0 too, right? That's the requirement for numbers to be allowed into this function. Make sense? So that's the same thing as x bigger than or equal to 4. So there you are, Evan. You have it in the chat as well. It can be anything above positive 4. And how do I write that as an interval? Well, that's what Stephen has. It's 4 to infinity with the open bracket around infinity. Very good. So that's what you're watching out for. If you're looking at square root problems, you're thinking, I can't have a negative inside that square root. So I would just take what's inside and say, I need that bigger than 0. And that's how I would do that one. What about, let's say, 1 over x minus 3? So, you know, sometimes it's nice to think of what number is allowed, like what we just did there. We said x minus 4, it has to be bigger than 0. Maybe this time the question is exactly, Lewis. The question is what's not allowed. 3 is not allowed because division by 0 is the problem here. So, okay, let me elaborate a tiny bit more on this one. Can take square root of negative number. Here what I'm worried about is dividing by 0. Can't divide by 0. So any number that would cause division by 0 can't be in the domain. It's not a number that the function allows. So as Lewis says, it can't be 3. So another way to write that mathematically would be that x minus 3 cannot be 0, meaning that x cannot be 3. Now, how would I write this in interval notation? So my solution. Anybody know how I would write this? I'll show you for this one. Yeah, no, interval notation I'm looking for, Stephen. It's going to be minus infinity to 3, union 3 to infinity. Okay. This describes every number except for 3 because I have the soft brackets, the open or soft brackets around 3. Any questions here? Okay, I'm almost finished with this, so I'm just gonna save me having to make a video and you just having to watch a video later. I'm just gonna go a little bit over time. What if we have the square root of x squared over x minus 4? What is a condition that I need here? This is kind of mixing up the two cases now, right? So in this case, x needs to be higher than 4. And the key part here is not equal to 4. We require both x minus 4, so we require x minus 4 greater than 0. This time, it's not greater than or equal to because, I'm writing poorly. It's in the denominator. Okay, so this means that x has to be bigger than 4. So our solution in this case, again, interval notation is what's needed for this section. 4 to infinity. And a slightly more challenging one to end on. Let's say we're looking at x over x squared minus 4. So this one, it's a similar thing, right? Before I get to the requirement and just kind of, as you look at this, you kind of think, okay, what do we need to do here? Think about which numbers work and which don't. If I have 2 in there, 2 squared is 4, 4 minus 4 is 0, it doesn't work. But numbers bigger than 2 work. 2, or 3, 4, 5, 6, 7, 8, 9, 10. They'll all be fine. 10 squared is 100, minus 4 is 96. Square root of 96, it's not pretty, but it works. Likewise, if I go negative with x, I don't really care what happens in the numerator, so just looking at the denominator, minus 3 squared is going to be 9, 9 minus 4, minus 4 squared, minus 5 squared. It seems like after negative 2 works as well. But only those small numbers where x squared is smaller than 4 won't work. So again, we require x squared minus 4 strictly greater than 0. So there's a few ways you can know how to do this. You can kind of know what the graph of this looks like and know where it dips below the x-axis. You'll be able to solve polynomial inequalities and know where things go 0. So x squared minus 4 is smaller than 0 when x is between negative 2 and 2. So these numbers are not in domain. So the solution is going to be minus infinity to minus 2 union 2 to infinity. Okay. That clear for everybody? Okay, so we're over time. If you have any questions, feel free to email them to me. I don't want to keep you much longer. Just a reminder that there's academic coaching today, and if you're in my section, it's going to be at 2 o'clock. You can find the link in the academic coaching course shell in Canvas. If you're not sure what section you're in, dig through your emails and try to find out any previous communication you had with continuous learning. If you really can't find anything, email Nicola from Continuous Learning and she can help you. And if it doesn't get sorted today and you were supposed to be in my section, then you can go to another section. Okay, any last questions before we go? Okay, well, if you're seeing me again at 2 o'clock, go get a snack or something. And also, I'm going to be expecting cameras on and participation. This isn't going to be like class where I'm kind of talking non-stop. It's going to involve you guys and break out rooms a bit more. So be prepared to have cameras and microphones on and participate. Quiz on Friday at the same time, yeah. Okay. Okay, take care, folks. I'll see you soon if you're in my section for a function. Good. Where's my cursor then? There it is.